Quite an exploration. It's one that might fundamentally challenge how you think about scale itself. We're going on a journey from the very biggest things we think exist in the universe, all the way down inwards to the smallest, most elusive concepts in reality. Just try to imagine a chasm so vast it almost defies comprehension. We're talking about something like 61 orders of magnitude. It's this dizzying gap separating the largest potential structure, the Hercules-Corona Great Wall, maybe 10 billion light years across, from the theoretical Planck length. And that's a point where space and time, well, as we understand them, they might just dissolve completely.
Yeah, in this deep dive, it isn't just about, cataloging sizes, not just a list. It's really a profound investigation into the very nature of existence. As we travel across these incredible domains, you'll find that the familiar laws of physics, they actually transform. The whole character of reality shifts, and the philosophical questions, about our place in it all, they become incredibly profound.
Right. Our goal for you, our listener, is to give you a real shortcut to being well-informed on this. You'll uncover some surprising facts, hopefully gain a deep understanding of what's truly important in this vast, mind-blowing subject. So, let's begin. We'll start our journey outwards to the grandest scales imaginable. You see, the universe isn't just some, chaotic scattering of galaxies. It's more like a meticulously crafted masterpiece of gravitational architecture. Matter is organized into this intricate web-like pattern, forming these colossal structures that are actually challenging the very boundaries of our current cosmological models.
That's a great way to put it. To give some perspective, this large-scale structure is often called the cosmic web. Think of it like the universe's skeleton, a vast interconnected network. You've got immense galaxy filaments, walls, sheets. These are collections of superclusters, and they're all interwoven with these huge, relatively empty expanses we call voids. And this pattern wasn't random. It was shaped over billions of years. You've got gravity pulling matter together, dark matter providing this sort of invisible scaffolding.
Right.
And then dark energy driving the accelerating expansion, pushing everything apart faster and faster. And believe it or not, it all started from these tiny infinitesimal quantum fluctuations back in the early universe. Inflation just stretched them out to cosmic size.
So we're talking truly gargantuan structures. Let's look at some examples, maybe starting closer to home. Our own galaxy, the Milky Way, is part of the Laniakea supercluster. Laniakea, that's Hawaiian for immense heaven, right?
That's right.
It spans about 520 million light years, contains, at least 100,000 galaxies?
Mm-hmm. And the mass is staggering. Over 100 quadrillion times the mass of our sun, something like 10 to the 17 solar masses.
And its boundaries aren't something you can just see, are they? They're defined by gravity.
Exactly. It's about the gravitational flow. All of those galaxies are moving generally inward towards a common center of mass we call the Great Attractor.
But the universe keeps surprising us. Recent surveys, they've uncovered even larger structures, haven't they?
They have indeed. Discoveries keep pushing the limits.
There's the Einasto supercluster, identified just recently, 2024, weighing in at 26 quadrillion solar masses, 360 million light years across, and the Kipu superstructure, named after that Incan record-keeping thing.
Yeah, the knotted strings.
That's a sort of filament-like arrangement, stretching for an incredible 1.3 to 1.4 billion light years.
That's enormous.
And then we get to the really controversial ones, the Huge-LQG, the large quasar group. That's a collection of 73 quasars, making a structure maybe 4 billion light years wide.
Yes, that one caused quite a stir.
But the current, maybe still debated record holder is the Hercules-Corona Great Wall, the HCB Great Wall, identified by this weird concentration of gamma-ray bursts. It's potentially a galaxy filament measuring an incredible 10 billion light years in length.
10 billion?
That's more than 10% of the diameter of the entire observable universe.
Precisely. And that scale immediately brings up some fundamental questions for cosmology. You see, our standard model of cosmology, it's built on this cornerstone assumption. We call it the cosmological principle.
Okay, what's that?
Basically, it posits that if you zoom out far enough on sufficiently large scales, the universe is homogeneous, meaning it's pretty much the same everywhere.
Right.
And isotropic, meaning it looks roughly the same in all directions.
Makes sense, like no special place or direction.
Exactly. And it's not just an abstract idea.
Yeah.
It's a practical necessity. It dramatically simplifies Einstein's very complex equations of general relativity. It lets us build workable models of how the universe evolves. Now, a direct consequence of this principle is that there should be a theoretical upper limit to how big coherent structures can be. This scale of homogeneity is estimated to be around, say, 1.2 billion light years.
Okay, 1.2 billion.
Beyond that scale, the universe should look smooth and uniform because, well, there hasn't been enough time since the Big Bang for gravity to pull together anything larger that's gravitationally bound.
So if the limit is supposed to be around 1.2 billion light years, what happens when we see something like the Huge-LQG at 4 billion? Or especially the HCB Great Wall at a staggering 10 billion light years? That sounds like, well, a pretty dramatic contradiction.
It's more than just a contradiction. It represents a potential crisis for the standard model of cosmology.
Yeah.
Seriously, if this foundational principle, the cosmological principle, is actually flawed, the consequences are immense.
How so?
Well, the mathematical models we use to describe the universe's expansion, its evolution, they might be an oversimplification, or maybe even fundamentally incorrect. The existence of structures that vast could imply that the initial quantum fluctuations, the seeds from which they grew, weren't as random or uniform as our standard theories of cosmic inflation suggest.
So it goes right back to the beginning.
Exactly. It could point to new, maybe unknown physics at play in the universe's very first moments.
Yeah.
It might force us to completely reevaluate our understanding of the universe's origins. It's a big deal.
Okay, wow. Let's pivot now. Reverse course completely. We'll journey inward from this macroscopic world right down into the heart of matter. And down here, the whole concept of size itself starts to get, well, incredibly ambiguous.
It really does. Our descent into the microcosm, let's start at the scale of the atom and its nucleus. We can zoom in on the proton, key component of atomic nuclei. It's not fundamental, remember, it's made of quarks.
Right.
Experiments trying to measure its size, they've given us a charge radius of roughly 0.84 to 0.88 femtometers.
Femtometers, that's incredibly small, a quadrillionth of a meter.
That's the scale, yes. 10 to the minus 15 meters.
And this is where we hit that proton radius puzzle I've heard about.
Exactly. For years, you had two independent methods, one using electron scattering, the other looking at the light spectrum from regular hydrogen. And they both consistently agreed on a radius of about 0.877 femtometers. Pretty
Okay, seems settled then.
Well, no. Then came a newer, much more precise technique using something called muonic hydrogen. You replace the electron with its heavier cousin, the muon, and this method consistently measured a radius that's about 4% smaller, around 0.84 femtometers.
4% smaller. That doesn't sound like much, but in physics.
In precision physics, it's a huge discrepancy, and it hasn't been fully resolved yet.
So what does this puzzle tell us about the idea of size at this tiny level?
It highlights something crucial. At the subatomic level, size isn't like measuring a brick. It's not a fixed, immutable property. It actually seems to depend on the probe you use, electron versus muon, and the method of observation, how you're looking at it.
Right. That's weird.
And it's a profound foreshadowing, really, of the even stranger rules that govern the truly fundamental particles.
So if we go past the proton, which is composite, we get to the elementary particles, things like quarks and leptons like the electron. These are supposed to be the basic building blocks, right? No internal structure.
By definition, yes.
Yeah.
Fundamental.
So do they even have a size in the way we think about it?
That's the million-dollar question. When physicists try to measure the size of these elementary particles, they encounter a completely new reality. Honestly, no experiment has ever resolved a finite size for an electron or a quark. Ever.
Really?
None. None. In our best theory, quantum field theory, they are actually treated as ideal dimensionless points, zero size.
But hang on, I've seen numbers, like experimental upper limits on their radius. Quarks less than 10 to the minus 19th meters, electron less than 10 to the minus 22nd.
Yes, those limits exist. They're incredibly small numbers.
Well, the question really shifts, doesn't it? From how big is it to maybe does it even have a size at all? What do those limits actually mean for something that's supposed to be a point?
It's crucial to understand this. Asking for the size of a fundamental particle like an electron. Well, in the language of modern physics, it's kind of a category error.
How so?
An electron isn't a tiny solid ball. Its size is more like the fuzzy extent of its probability cloud, the region where you're likely to find it. See, according to quantum field theory, or QFT, the universe isn't fundamentally made of particles. It's made of fields, everywhere.
Fields, like magnetic fields.
Sort of, but more fundamental. There's an electron field, a quark field, a photon field, permeating all of space. What we perceive as a particle, like an electron, is actually just a localized, quantized excitation, basically, a ripple or vibration in its corresponding field.
Okay, a ripple in a field.
Exactly. So when an experiment sets an upper limit on the electron's radius, say 10 to the minus 22nd meters, it's not measuring a physical boundary.
Oh.
What it's really doing is confirming the robustness and the domain of validity of our current theory, the standard model. It's saying, look, down to this incredibly small scale, the theory describing the electron as a point-like ripple in its quantum field holds true.
Wow. Okay, so the size is really the limit of our theory working.
In a sense, yes. It's the scale down to which the point-particle description is experimentally verified.
This is heading somewhere really strange, which I guess brings us to the ultimate frontier, right? The Planck scale. This is the realm so incredibly small that our established theories, they completely break down.
That's the idea. The Planck length. It's approximately 1.6 times 10 to the minus 35th meters. It's generally considered the smallest meaningful unit of length in theoretical physics.
Meaningful how? Is it just a really small number someone picked?
Oh no, not at all. It's not arbitrary. It's derived uniquely from combining the three most fundamental constants of nature. You take the speed of light, geese, which governs relativity, the gravitational constant, g, which governs gravity, and the reduced Planck constant, phi bar, which governs quantum mechanics.
The big three.
The big three. Combine them in the only way that gives you a unit of length, and out pops the Planck length. Its unique origin from these constants, which define both general relativity and quantum mechanics, gives it this profound significance. And this scale, it's often called the wall of physics. Why? Because it marks the point where the predictions of general relativity, our theory of gravity and spacetime, and quantum mechanics, our theory of the very small, become irreconcilably contradictory. They just give nonsense answers when applied together at this scale.
They fight each other.
They completely break down. To describe reality at this scale or smaller, you absolutely need a unified theory, a theory of quantum gravity. We don't have a proven one yet.
Okay, I heard there's a thought experiment about this involving black holes. How does that work?
Ah, yes, it's a classic. It beautifully illustrates the problem. According to Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, to observe a very small region of space, you need to use a probe with very high energy. A very high-frequency particle, basically. The smaller the region, the higher the energy needed.
Okay, makes sense. Like a powerful microscope.
Exactly. But here's the twist from general relativity. Einstein's theory tells us that if you concentrate enough energy or mass into a small enough region, its gravitational pull becomes so intense that it collapses into a black hole.
Whoa.
So combine these two ideas. If you try to observe a region of space smaller than the Planck length, you'd need a particle with such incredibly high energy that the energy itself would, according to GR, create a microscopic black hole right at the spot you're trying to look.
And the black hole would. What?
It would instantly swallow your probe, your observation, effectively hiding that region of spacetime from view.
So you literally can't see smaller than the Planck length because trying to look creates a black hole that blocks the view.
That's the essence of the thought experiment. It's like the universe itself has a fundamental pixelation, or resolution limit, imposed by the combination of quantum mechanics and gravity. It's saying you cannot probe distances smaller than this.
Wow, that is mind-bending. So what does spacetime even look like down there?
Well, the description that often comes up is quantum foam. Imagine space-time itself, at that scale, isn't smooth and continuous like we normally think. Instead, it's this roiling, chaotic sea of virtual particles popping in and out of existence, tiny fluctuations in geometry, maybe even virtual black holes constantly forming and evaporating.
Oh.
A bubbly, foamy structure.
Quantum foam, okay. And to try and actually describe this mathematically, we need those theories of quantum gravity you mentioned.
Exactly. We need a new framework. And the two leading candidates, they offer radically different pictures of this ultimate reality.
Let's touch on those. String theory is probably the most famous one.
It is. String theory proposes that the point-like particles of the standard model, the electrons, quarks, photons we talked about, are actually just a low-energy approximation.
Yeah.
In this framework, the universe's ultimate constituents aren't points at all. They're unimaginably tiny, one-dimensional vibrating strings, and they exist roughly at the Planck length scale.
So everything is made of tiny, vibrating strings. What does that imply for all the different particles we see? Are they different kinds of strings?
No, and that's the elegant part. The truly profound implication is that all the different elementary particles we observe, electron, photon, quark, gluon, everything, they're simply different vibrational modes of a single underlying type of string.
Like notes on a guitar string.
Exactly like that.
Right.
It's like a cosmic instrument. Different notes, different vibrations manifest as different particles with different properties like mass and charge.
Yeah.
It's a potential path to unification.
Okay, that's one picture. What about the other main contender, loop quantum gravity, LQG?
Loop quantum gravity takes a fundamentally different approach. Instead of positing new entities like strings living within spacetime, LQG attempts to quantize spacetime itself. It applies the principles of quantum mechanics directly to the fabric of reality.
Quantized space-time, what does that mean?
It means space-time isn't a smooth, continuous background. LQG postulates that space itself has a discrete atomic structure at the Planck scale. It's woven from finite quantum loops or connections, creating structures called spin networks. And as these evolve in time, they create spin foams.
So space is like pixelated, made of tiny bits.
In a very abstract mathematical sense, yes.
Mm-hmm.
And in LQG, it becomes truly meaningless to speak of anything smaller than the Planck scale. Because space itself, in the continuous sense we're used to, simply ceases to exist below that fundamental granularity. There is no space for something smaller to exist in.
Wow. Two very different ideas about the ultimate nature of reality.
Radically different mathematical structures and conceptual frameworks, both trying to bridge that gap between GR and QM. So just to reiterate the incredible span we've covered here, this journey from the cosmic to the quantum. We went from the largest putative structure, the HCB Great Wall, measuring maybe 10 to the 26th meters, all the way down to the smallest theoretically meaningful length, the Planck length, at roughly 10 to the minus 35th meters.
That difference. 61 orders of magnitude. It's just impossible to really visualize.
It really is.
I heard an analogy once. If you scaled up a single atom to be the size of the entire observable universe, then the Planck length on that new enormous scale would only be about the height of an average tree.
That's a fantastic analogy. It captures the sheer absurdity of the scales involved.
The universe is mind-bogglingly vast, and yet, even within its tiniest conceptual units, it remains equally mind-boggling.
And this vast journey, it reveals a really profound conceptual shift, I think. At the Planck scale, the fundamental ontology of the universe, what it's made of, appears to change completely. Those familiar concepts we use, like substance, particles or fields and the stage they play on space-time, they seem to lose their primary status.
Right, like the black hole thought experiment showed.
Exactly. The distinction between the observer, the thing doing the measuring, and the observed. The thing being measured. That distinction becomes untenable. You can't separate them. And interestingly, both leading theories of quantum gravity, string theory, and LQG seem to resolve this by positing a deeper, more abstract reality, one based on, well, pure structure, information, relationships, mathematics.
So the ultimate answer to what is smaller than a quark isn't just a smaller thing.
Probably not. It might be a different category of existence altogether, where matter and space aren't fundamental but emerge, like two sides of the same coin, from some underlying, perhaps purely mathematical or informational reality.
Okay. This grand tour across all scales, from the cosmic horizon right down to the quantum foam, it's not just a scientific exercise, is it? It forces us to bump up against these really deep philosophical questions about knowledge itself, about existence, about where we fit in.
Absolutely. And there's a remarkable symmetry, I find, between the limits of our observation at both extremes of scale.
How so?
Well, at the largest scale, our view of the universe is fundamentally incomplete, right? We're bounded by the cosmic event horizon stuff so far away its light hasn't reached us yet, and we're bounded by the wall of the cosmic microwave background, the earliest light we can see. So our knowledge of the whole is necessarily partial. We can't see everything.
Okay. And at the smallest scale?
At the smallest scale, we hit a different kind of limit. The Heisenberg uncertainty principle, the observer effect. They mean that the very act of measuring something irrevocably disturbs it. Our knowledge of the parts is fundamentally probabilistic, fuzzy. We can't know everything about a particle's state simultaneously with perfect accuracy.
So we're limited looking out and limited looking in.
In different ways, yes. And what this tells us, I think, is that these twin limitations, they place the observer us right at the center of the reality that's being described. The universe we model, the physics we discover, it seems inextricably linked to the fact that we are here to model it, to observe it.
That's interesting because contemplating the sheer vastness of the cosmos, those billions of light years, it often makes people feel, well, profoundly insignificant. That feeling of being a tiny speck on a tiny rock in this indifferent, immeasurable void. It's a very common understandable reaction.
It is understandable, but there's actually a powerful counter-narrative to that feeling of insignificance. It's found in something called the anthropic principle.
Ah, the anthropic principle. Can you break that down?
Sure. Let's take the weak anthropic principle, or WA. It basically states that the properties we observe the universe to have, its age, its physical laws, its constants, they are necessarily constrained by the requirement that they must be compatible with the existence of observers like us.
Okay. So we see the universe the way it is because if it were different, we wouldn't be here to see it.
That's the core idea, and the implication is profound, especially regarding scale. Think about the universe's immense age, about 13.8 billion years, and its vast size, billions of light years across. These aren't necessarily arbitrary. For example, the heavy elements essential for life, carbon, oxygen, iron, and roofing, they weren't made in the Big Bang. They had to be forged inside stars over billions of years, then scattered by supernovae.
Right. Stellar nucleosynthesis takes time.
Exactly. It takes billions of years. So a universe capable of supporting life like ours must be billions of years old. And a universe that's expanding, as ours is, and is billions of years old, well, there must also be billions of light years across. The expansion guarantees it.
So the vastness isn't just incidental to our existence.
This perspective completely reframes it. We are not just an insignificant accident floating in the universe that happens to be huge. Rather, the universe's vastness, its age, they might be direct and necessary preconditions for our being here at all. It becomes a testament, really, to the extraordinarily precise and intricate set of conditions required for complexity, life, and ultimately consciousness to emerge.
That's a very different way to look at it. Not insignificance, but connection, precondition.
Connection contingency, perhaps.
Wow.
It highlights how special, in a scientific sense, the conditions for our existence are.
And this line of thinking, connecting physics with these bigger questions, it leads us towards what many call the ultimate scientific quest, doesn't it? The quest for a final theory, a theory of everything. That seems like a true synergy of physics and, well, philosophy.
It absolutely is. This quest, it's seeking an ultimate explanation for reality itself. A self-contained mathematical model, ideally, that could answer the most fundamental questions. Questions like, why are the laws of nature as they are? Why these specific forces, these particles, these constants, and perhaps even touching on that ultimate metaphysical enigma. Why is there anything at all? Why is there something rather than nothing?
Heavy stuff.
It is. And this journey to the frontiers of knowledge, both outward and inward, it reveals that the boundary between physics and metaphysics, it isn't some sharp, impermeable wall. It's more like a porous membrane. You take something like the fine-tuning problem in cosmology. That's a physical observation. The fundamental constants of nature seem exquisitely balanced, almost fine-tuned to permit life.
Right. If gravity were slightly stronger or the electromagnetic force slightly different.
Exactly. The universe would be radically different, likely sterile. Now, that observation demands an explanation. But the proposed explanations appealing to the anthropic principle, maybe invoking a multiverse where all possibilities exist, these are explanatory frameworks that, what rooted in science, definitely venture into territory that feels philosophical, even bordering on metaphysical.
So the science itself pushes us into these deeper philosophical waters.
It seems unavoidable when you push the boundaries far enough.
What an incredible, a 61 order of magnitude odyssey we've just been on. From the largest cosmic structures, maybe challenging our basic assumptions about the universe, down to the theoretical smallest length where space-time itself might dissolve. The very character of existence, it truly transforms across these scales. We started with that, classical gravitationally sculpted cosmos, then plunged down into matter where the solid certainty is just dissolved into fuzzy, probabilistic clouds of quantum mechanics, and then finally into the abstract reality of quantum fields, maybe even vibrating strings or loops of space-time itself.
It really reinforces this idea, doesn't it, that the universe we inhabit isn't monolithic. It's like a multi-layered tapestry, and different physical laws, different conceptual frameworks are needed to understand each successive scale. What works up here doesn't necessarily work down there.
And this whole human endeavor, trying to measure and model and comprehend this full spectrum of reality, it just continuously pushes the boundaries, doesn't it, of science, of technology, and even of philosophy itself.
It really does. And perhaps in the end, in charting the full scale of existence, from the unimaginably large to the unimaginably small, we ultimately chart the limits and maybe even the potential of the human mind itself.